In this video, we'll be talking to you about Experiment 1. In Experiment 1, you'll be measuring the mass and volume of several objects in order to determine their density and their identity. We're also going to be thinking about error and different sources of error from our measurement tools. Let's first talk about the error. So error comes from mistakes in computation, deviation from the true value, or incorrect observations. Typically, what we're really interested in when we're thinking about error is when we're thinking about systematic error that comes from the measuring tools. Error is thought of as the absolute value of the measured minus the true value. We can also calculate what's called the percent error if we compare the measured and the true against the true, and usually this is reported as a percentage. When we're thinking about calculating error, the equation's fairly straightforward. What usually gives students some difficulty is thinking about the sig figs. So, because the equation has us thinking about doing subtraction first, followed by division, we're going to first follow the subtraction rules, then division rules for significant figures. Let's look at an example. If a student measures a block and finds that the density is 8.445 grams per centimeter cubed, and the value found in the table indicates that the block has a density of 8.43 grams per centimeter cubed, let's calculate the error for the measurements using correct significant figures. So the first part of the equation has us taking the absolute value of the measured minus the true value. The measured value is 8.445. This value has 3 decimal places. We are going to subtract the true value of 8.43. This is what was found in the table, and this number has 2 decimal places. So when we use the significant figure rules, when we do subtraction, we go by the fewest decimal places. In this case, we should report 2. So we do our subtraction, and we get a value of 0.015. If we only report this value with with 2 decimal places, we'll see that this number only has 1 significant figure. So now we're going to do our second step, which is finding the percent error, and that's where we take our absolute value of the measured minus true, so 0.015. We're not going to truncate this value. We're just going to note that it only has 1 significant figure, and we'll divide by the accepted value of 8.43, and then we'll multiply by 100%. So because this number, after we did our subtraction, only had 1 significant figure, we'll report our value with just 1 significant figure, so we get 0.2%. And that's how you use significant figures with error calculations. Another source of error that you might have happen in your measurements is what we call relative error or uncertainty. And this relates to error in a numerical value due to our measuring device. So, depending on the tool that you're using, you will have different uncertainty values. So this varies by device or measuring tool or whatever instrumentation you're using. So this is not a constant value. Okay? Typically, this is reported as a plus or minus value. So most instruments, including burettes, pipettes, even balances, will have a plus or minus value when you look at them. Typically, pipettes will have something like plus or minus 0.05 milliliters. And this comes directly from the manufacturer. They tell you how precisely you can measure different volumes in their pipettes. Most balances, especially the ones we use, will have plus or minus values of 0.001 grams, meaning that the last digit that you see or read off of the balance will actually be kind of a small range of values, and we're not really certain what that last digit is, but we can get fairly close to it. So we can calculate a relative error, which is where we take that uncertainty reported on the instrument, which is our plus or minus value, and we divide that by our measured value, times 100%. So if we ask you any questions where we say something like, if the mass of an object was determined to be 1.250 plus or minus 0.001 grams, what is the relative error in the measurement? You would say, well, I know that the relative error is equal to the uncertainty, or the plus or minus value, which is 0.001, divided by the value that I measured, 1.250, times 100%. This will only have one significant figure because uncertainty should only be in one of the decimal places, and we'd get an uncertainty of 0.08%, which is fairly small. So we know that the measurements that we're taking are going to be fairly precise with a small relative error. So that's how we think about error. Let's talk about the measurements that you'll be taking when you do this experiment. The first is mass. So we think about the amount of matter in a given object. To measure the mass, we're going to be using balances. When you use the balance, you're going to start by pressing 0, and when you do, the balance should read 0.000 grams. If you need to, you should obtain the mass of the container. This is something you'll do if you're measuring a liquid or an irregular object. Then you'll place the sample in the container and obtain its mass. So, to obtain the mass of the sample, you would just take the mass of your container plus the sample and just subtract the mass of the container. If you have a solid, a block, or something else that doesn't need a container, you can just put your sample directly on the balance. And you'll record all the digits that you see on the balance. There's no need to do any rounding. We want to use all of the numbers that the instrument gives us so we have an accurate reading. The other measurement we're going to be taking or calculating in this experiment is volume. So there are two ways that we're going to think about volume in this experiment. One is by water displacement. This is a really easy thing to do if you have an irregular object where it's not easy to measure its dimensions. So we're going to use this for our irregular solid. For a typical sample, like a block or a cylinder, it'll be easy for us to measure its dimensions. So we will use this for our blocks. There are two of them, and for our cylinder. We are going to be using calipers in order to do this. Our calipers in lab measure in millimeters. We want to convert this to centimeters so that our measurements match the values in the table that we'll be comparing them to. So anytime you take a measurement in millimeters, you can just divide by 10 to get that number in centimeters, and you're welcome to do that mental math in your head and just write down your values in centimeters on your data sheet. Then we need formulas for a block or a cylinder or a sphere so that we can take our dimensions and get them to what we need. So for a block, we're going to do length times width times height. For a cylinder, you will use pi r squared times the height, where r is the radius. So you won't be able to measure the radius directly, but you can measure the diameter and divide by 2. And we know the volume of a sphere is 4/3 pi r cubed. You won't be measuring any spheres in lab, but that's a helpful equation to have if you have any questions like this after you finish the experiment. Once we've measured the mass and the volume, we are going to calculate the density. The density is the ratio of mass over volume. So, you have a mass, you have a volume, and you just take the ratio, m over v. And this will have units of grams per milliliter or grams per centimeter cubed, depending on which object you measured. These two units are equal because 1 milliliter is equal to 1 centimeter squared, or centimeter cubed. We know that mass and volume are extensive properties that are based on how much sample we have, but density is an intensive property. And because it's an intensive property and it's not dependent on how much sample we have, we are going to use this to identify the sample. And you will have tables within Experiment 1 that tell you what the densities are of different solids, and you'll be able to compare it to the values you calculated so that you can identify the different objects.